Parallel computing is a basic question in computer science, I think, from the beginning, just because in sequential computing we're so satisfied that the Turing machine von Neumann duality has been so successful. So the question is whether one can do parallel computing as successfully in that general purpose way and as easily. So this has always been around. So I suppose there are two main stages in my work on this. So the first one was to do with the communication, that the main problem, the first problem you have to overcome is one of communication, that computation you can do locally, but if you want to communicate among lots of processes, that's the bottleneck. And so actually on this point, that's clearly also a bottleneck in the brain. Communication is just a bottleneck in any kind of parallel computing. So I worked on this problem of routing, and so it was related to queuing theory. So queuing theory existed where you got lots of people in queues, but queuing theory concentrated on just the average, what the average wait time of a single person is, whereas here the issue is that you're trying to route a large number of packets, and what's important is when the last one arrives, because that's when you can start the next step. So then this problem had a positive solution. So I think I thought of publishing a paper called "Parallel Computing is Possible," but then in fact, the routing was somehow more general communication, so I gave it a more general title. So this was one phase. And so this was about 1980. And then, so after that, built up a picture of what a parallel computer would be, which would be having some big network, having some good general purpose routing thing, and then maybe at a high level you simulate a nice programming language like a PRAM is an abstraction where the programmer doesn't have to worry about locality. But there's still was something missing there, and because even if you could do all this, somehow it didn't lead to paradise. Somehow things were still difficult. And as far as recollections, I remember going to a meeting in that was probably in late 1988 in California on parallel computing, and in parallel computing, everyone comes and says their own. Describes their own angle, but there's never any summary. And I remember thinking, that of the things said here, I think all the important things are already known and have been said, but somehow we don't understand. We don't understand it hasn't been encapsulated. And then at the same time, I'd volunteered to write an article for this handbook of computer science, which was edited by Van Leeuwen, did one on parallel computing. So although normally I hate writing these summary things, I thought this would be good for me, because I knew that this field was totally in chaos in my own mind. Right. So I thought it would be good for me to organize it in my own mind. And also, so there was just a plethora of models of parallel computation at the time. So the idea that one needed a new one, that seemed the worst idea. So no one thought you needed a new one because there were so many already. But this Synchronous model actually came out, again, kind of by accident. I was sitting at a desk, and I was literally trying to do reductions between various models. So this model reached this model efficiently. And then I did a few of these, and there was this thing in the middle, okay? And that was the Synchronous model. And the one miraculous aspect was that this wasn't one of the 1,000 models already known, so it was a bit different. So I thought maybe it meant something. So that's how I came to that. So it's so what it is so I call it a bridging model. So one thought that I had at the time was that I was about 40 years old, and I was a computer scientist that never thought carefully about the difference between a Turing machine and the von Neumann model. So I thought this was shocking. That how come not? So I did think about it, and then the interpretation I came to was that the Turing machine is some pure mathematical model. It's here to stay. It's perfect for what it is. while the von Neumann model is more a kind of a pragmatic thing, which is influenced by physics. So the amazing thing about the von Neumann model is that even as technology changed, you could implement it efficiently over the decades. And then I thought this was the paradigm to which parallel computing should aspire. So part of the bulk synchronous model is that it's a pragmatism which is possible in physics.